Hi, this is a video for section 4.5, which is solving exponential and logarithmic, solving exponential and logarithmic equations. Those are the only two learning targets here. We'll first look at solving the exponential equation, and then we'll look at solving a logarithmic equation. And you'll probably want to pause this periodically to write stuff down. Make sure you get the problem written down before I start solving it. So go ahead and be ready to hit pause every now and again so you can get everything down there. We'll first look at solving exponential equations. You can really break it down into these three steps. Let's go ahead and pause it so you can write these three down, but it's isolate the exponential term, use logarithms on both sides to cancel the base, and then solve for x. So looking at an example here, step one says to isolate the exponential term, so it's important that you can first identify the exponential term and to isolate it. The exponential term is the term that contains the base with the exponent that has the variable. So this right here would be the exponential term that's got the base and the variable exponent. So a first step is to isolate that, means get it by itself on that same side of the equation. So I'm going to go ahead and isolate it by adding 3 on both sides. And you get 2dx plus 1 is equal to 6. So now the exponential term is isolated. So we're down to step 1. Step 2 is now to use a logarithm on both sides. What we need to do is get this out of exponential form into logarithmic form. This is what we practiced back in section 4.3. And in order to get this out of exponential form, we need to cancel a base. And we all know what cancels bases: logarithms. We use a log base 2 on both sides. And now that x plus 1 is no longer an exponent, it's just x plus 1 equals log base 2 of 6. So now we've taken care of step 2. We've used logarithm on both sides. Step 3 now is to solve for x. So all we need to do now is subtract 1 on both sides. And one mistake I see every now and again is students will try to subtract or add to that number inside the logarithm. You can't do that. This minus 1 is outside the function, and the 6 is inside the function. So it does need to be written like that. You can't combine that into log base 2 of 5. That's a different number. So this would be the solution. Now often textbooks and on an exam may ask for different versions of the answer. This one here is what's called the exact form. Exact form means leaving it in terms of a logarithm. If they want the approximate form, then you're going to have to figure out what this equals on a calculator. And we did talk about this in class, that most calculators can't do logarithms with base 2 or base 3. The only ones they can do is log base 10 or the natural log. So to put this into a calculator, we would need to use the change of base formula that we talked about in section 4.4. So log base 2 of 6 can be rewritten as log 6 over log 2, and then we can subtract 1 from that. And then on a calculator, if we did log 6 divided by log 2, and then subtract 1 from that, we're going to get 1.58. So this would be the approximation, 1.58. And it's pretty much those same 3 steps for most exponential equations. You isolate the exponential term, use a logarithm on both sides, and then solve for x. So part B here, we need to identify the exponential term first before we can isolate it. The exponential term in this problem is 4 to the x minus 1. So to isolate that, we're going to need to subtract 2 And then that 3 in front is multiplying it. It's a coefficient, so the opposite of multiply would be divide. I do see every now and again students try to combine these two numbers by multiplying and turning that into a 12. That doesn't work either. That's not following order of operations. You can't multiply those two numbers together. But you divide by the 3, and you get 4 to the x minus 1 is equal to 4. So now we are to step 2, which is use a logarithm on both sides. In order to cancel a base 4 here, I'm going to use a log base 4 on both sides. So on the left there, we're just left with x minus 1. And the nice thing about this problem is this also cancels nicely. This happens every now and again. But log base 4 of 4 is just equal to 1. If you add 1 on both sides, you get x equals 2. You will see some exponential equations involving base e, or the natural number. But it's no different, same 3 steps. We need to isolate the exponential term. So in this case, e to the 2x plus 1, that is the exponential term. In order to isolate it, we're going to divide by 3. So we have e to the 2x plus 1 equals 7/3. Now to cancel a base e, we're going to use natural log on both sides. Natural log cancels base e. So we have 2x plus 1 equals the natural log of 7/3. Now we are to step 3, which is solve for x. So we're going to subtract 1 on both sides, and then divide everything by 2. So the exact form of this answer would be natural log 7/3 minus 1 divided by 2. And again, if the textbook or exam asks for the approximate form, then you would plug this into a calculator, figure out the approximate form. So we're going to move on now to solving logarithmic equations. So solving logarithmic equations contains very similar steps to solving exponential equations. First thing we're going to do is isolate the logarithmic term. We can't cancel a logarithm until it's isolated, meaning it's the only thing on that side of the equation. Once we have the logarithm isolated, then step 2, it's called exponentiate both sides. Really, that just means use a base on both sides to cancel a logarithm. We talked about this back in section 4.3. What cancels a logarithm is a base that matches the base of the logarithm. That's called exponentiate, when you use a base on both sides. And then once you've gotten rid of the logarithm, you can solve for x. So go ahead and pause if you need to and write down those 3 steps into your notes. Okay, example 1 here. Step 1 would be to isolate the logarithmic term. So the logarithmic term obviously includes the logarithm and what's inside of the logarithm. So log base 2 of x plus 3, that's considered the logarithmic term. So to isolate it, we're going to add 1 to both sides. Log base 2 of x plus 3 is equal to 6. Now we're to step 2, exponentiate on both sides. That means just use a base that's going to cancel the logarithm. In this case, we're going to use a base of 2. And it doesn't seem like a big deal, but it's critical on how you write this. Make sure you write this in a way that you realize it's 2 to the power of 6 and not 2 times 6. I see students confuse that. Write it in a way where it's clear to you that the base is 2 and the exponent is 6. Over here, 2 base and the log base 2 cancel, so we're left with x plus 3 is equal to 2 to the 6th power, which is 64. And now we're to step 3, which is solving for x, and we get x equals 61. Another example here. Step 1 is to isolate the logarithmic term. Before sometimes you can isolate it, you need to identify what is exactly the logarithmic term. In this case, it's the natural log of x minus 4. That's the logarithmic term. So to isolate it, we need to subtract 3. And then that 4 is just a coefficient in front of a logarithm, multiplying it. So we're going to divide by it to get rid of it. So that leaves natural log of x minus 4 is equal to 5. Now we've isolated the logarithmic term, so the next step is to exponentiate on both sides using a base that's going to cancel that particular logarithm. In this case, we need to use a base e. And a base e cancels a logarithm, a natural logarithm, so we have x minus 4 equals e to the 5th. And to get x by itself, we're going to add 4. So x equals e to the 5th plus 4. This, as with some of the problems we've done, this would be considered the exact form of the solution. If the book or test asks for the approximation, you would type this into your calculator and get the approximation. Now, you're going to see a little more variation in logarithmic equations than with exponential equations. Quite often, with that step 1, isolate the logarithmic term, often that means condensing multiple logarithms into a single logarithm. That's why we practiced that skill in section 4.4. You can see from this example here, we have 2 logarithms. If 2 logarithms are on the same side of the equation, you can't solve that equation. So step 1, isolate the logarithmic term. In this case means instead of dividing by things on both sides or adding or subtracting things on both sides, it's actually condensing these 2 logarithms into one single logarithm. And this would be an example, since there's an addition symbol between the two, this would be an example of the product rule that we saw in 4.4, where the x plus 2 and x minus 1 are going to multiply. So we've isolated now the logarithm. We've taken two separate logarithms, condensed it down into a single logarithm. Now we can do step 2, which is exponentiate on both sides. So this is a common log. Since you don't see a base here, we know it's base 10. So if I use a base of 10 on both sides, I'm going to have x minus 2. I keep saying minus 2. X plus 2 times x minus 1 is equal to 10 to the first power, which is 10. Now we're stuck with a different sort of equation to solve for x. We're to step 3, solving for x. Problem is, this is not your typical linear type equation to solve for x by simply adding or subtracting or dividing by a few numbers. What we have is a quadratic, and if you remember, we've solved several quadratics so far in this course. The only real way you want to solve a quadratic equation is if it equals 0. This does not equal 0, it equals 10. So what you're going to need to do is multiply that left side together. So we got x squared plus x minus 2. Now I can subtract 10 and get x squared plus x minus 12 is equal to 0. So now that we have a quadratic equation equal to 0, we can solve the quadratic equation, and there's really 2 ways we've been using in this course to solve quadratic equations. One way is by factoring, the other way is quadratic formula. This one, luckily for us, factors to x plus 4 times x minus 3. And x plus 4 multiplied by x minus 3 equals 0, means that x plus 4 has to equal 0. And x minus 3 equals 0, therefore x equals negative 4. and x equals positive 3. Now, at this point, we've got two different possible solutions. You need to remember something that we talked about back in section 4.3, the domain of a logarithm. You cannot take the logarithm of negative values. This is part of that domain restriction we talked about. This is why logarithmic graphs have a vertical asymptote. You can't take the logarithm of negative values. That doesn't mean your solutions can't be negative. What that means is if you plug it in to check the solutions, it can't stay negative. For example, if I plug in the negative 4 right here for this x, I get negative 4 plus 2, which is negative 2, so I'd have to evaluate the log of negative 2. That's impossible. You can't evaluate the logarithm of a negative value. So what we conclude from that is negative 4 isn't actually a solution. The other one was positive 3. We got to make sure to check that one as well. If I plug in a 3 here, I get 3 plus 2, which is 5. That's fine. If I plug in a 3 here, I get 3 minus 1. That's 2. That's also fine. So x equals negative 4 doesn't actually work. It's outside of the domain. X equals 3 is the only solution. The textbook uses a word here for these types of solutions that don't actually work. It's called extraneous. You don't need to write that down, but x equals negative 4 is extraneous. Okay, a different look here at an equation involving multiple logarithms. This one has 3 now. Where you're going to run into trouble is if you have multiple logarithms on the same side. Like this, we have 2 separate logarithms on the right side of the equation. That we want to avoid. So what we need to do is condense that into a single logarithm. And again, because of this plus sign here, this is another example of the product property. So the x minus 2 and the x plus 3 form a product. Okay. This one's a little different from the last one, where we now have logarithm on each side, but the key here is we have a single logarithm on the left side and a single logarithm on the right side, and they both have the same base. So step 1 now is actually done. We've isolated logarithms on each side. There aren't multiple logarithms, and there's no coefficients, there's nothing adding or subtracting to any of them. So in this case, we have one single logarithm that equals one single logarithm. So we can move on to step 2, which is to exponentiate both sides. If we go ahead and use a base 5 as a base on both sides of the equation, that's going to cancel the logarithms, leaving x squared plus 1. And I'm going to go ahead and multiply these two together to get x squared plus x minus 6. And again, this seems like it might be a quadratic equation, and so the only way that you want to solve a quadratic equation is to get one side equal to 0. So I'm going to subtract here and get 0 equals, but now the quadratic terms cancel, so we have x minus 7. Adding the 7 back over gives us x equals 7. But one thing you're always going to want to check is, do you have an extraneous solution? So if I plug in a 7 here, for example, I get 7 squared plus 1, that's 50, so that's fine. If I plug it in here, 7 minus 2 is 5, and that's okay. If I plug it in here, I get 7 plus 3, which is 10, that's okay as well. So x equals 7, seems like it's going to work. And that there does it for solving exponential and logarithmic equations.